Okay, so welcome everyone to Swapnil Baral's PhD defense. The whole committee is here. We've got Lars Gundlach from University of Delaware Chemistry, Björn Baumeier at TU Eindhoven, who is Swapnil's co-advisor, Sandeep Patel, University of Delaware Chemistry, and Jim MacDonald, University of Delaware Physics. So Swapnil joined us here in the UD Physics program, Physics and Astronomy program, in the fall of 2014. He joined my research group in summer of 2015. He's been working on a sophisticated QM-MD method for computing spectral properties of a certain class of chemical probe that's used to study membrane structure and dynamics. And he got his first paper out of his research earlier this year in Journal of Physical Chemistry B. It was a really great synthesis of theoretical work directed by myself and Björn and experimental work done in the lab of Lars. And he's got another manuscript which is currently in revision, and a third one which is in a pretty late stage of preparation. So he's been quite productive. Before I turn it over to Swapnil, I would just like to say to everybody on the committee who's on the Zoom link to please mute your microphone. And to other people watching on the YouTube stream, if you would like to ask questions, you can type them in the chat window of YouTube, or you can email them to me at lyman@udel.edu, and I'll monitor both, and then I'll relay the questions to Swapnil at the appropriate time at the end of the talk. And then at the end of the talk, we'll switch to a private feed. Okay, so great. Please, Swapnil, go ahead and take it away.
Hello, everyone. Normally, like my family members normally ask me, what do you do in the grad school? What have you been working on? How long does it take to graduate? So today, I will be presenting the work I've been doing for past 5 years since I joined the Lyman group in 2015. And I'm glad my family members are watching the YouTube stream from Nepal and also from California, Texas, and perhaps also from Canada. I will motivate the discussion by talking about different kinds of lipid bilayers and different kind of phases these lipid bilayers can be in. And I will explain how we can use a polarity sensitive dyes to study about these lipid phases. I will state my research goal. I will describe the method very briefly. Then I'll present the result of the simulation and the calculation I have ran, both in simpler system and more complicated lipid system. Then I will present the result of the free energy calculation that I have run, and finally summarize. Animal cell consists of different kinds of cell organelles, all of which are enclosed by a membrane known as a cell membrane. In a very simple representation, a cell membrane can be represented by two layers of lipids, and this is known as a lipid bilayer. Lipids have a love-hate relationship with a water molecule. So basically, each lipid molecule can be categorized into two categories. One is the head group region, which is highly polar and they likes to interact with the water molecule and they are hydrophilic. Whereas the tail region is a fatty acid tail made up of hydrocarbon chain. They are non-polar and they likes to stay away from the water molecule. Therefore, what happens is these lipids self-assemble by orienting all the head groups towards the water and the tails away from the water, forming different kind of structures, and one of which is the lipid bilayer. The cell membrane is highly complicated, heterogeneous, made up of hundreds of different kinds of lipid species and proteins. Now, some of the key questions in the field of lipid research are, why are there so many different types of lipids in the membrane? And why do these types, the mole fraction of these types vary from one kind of membrane to the other kind of membrane? In 2001, Hegelman mentioned the upcoming decade as a decade of lipid research. And in 2006, Bagatoli mentioned by knowing about lipids, there could be the explosion of information. So what I am going to present today is my attempt of being the part of this journey. So even though the cell membrane is highly complicated, so what we do on our computer is we simulate, we study a very simpler system that consists of a few different lipid types. These are the lipid types that are involved, and they are relevant to today's discussion and to my calculations. Here is the name of the acronyms, abbreviation I have used, and there are different kinds of lipids here. But with the exception of cholesterol, in much of these lipids, we can find some similarities. All of these have a nitrogen in the head group. They also have a phosphate in the head group. And this head group region is connected to the tail region by a backbone, and they all have a fatty acid hydrocarbon tail. Now, there are also some differences between these different lipid types, some of which are the length of the hydrocarbon chain, the presence of unsaturation on the bond, which has a very interesting effect because the presence of this unsaturation provides a kink to the lipid tail, which increases the randomness of the membrane. It increases the area of the membrane, providing more free volume in the vicinity of the lipids between each other. Now, the another lipid here is a cholesterol. Yes, cholesterol is also a lipid. Is an interesting molecule. It's like consists of a hydroxyl 4-fused ring, and it has very interesting effect in the lipid membrane. And this constitutes an important composition. It's like 20 to 40 mole fraction of the membrane is a cholesterol. The simplest of the simplest system we can think of the lipid bilayer is a one component bilayer. This is like a single component bilayer, which consists only one type of lipid. If the temperature of this lipid bilayer that has only one kind of lipid is below the melting temperature, we have this bilayer in a gel phase. This is also known as a solid phase. So basically, in this phase, all of these lipid tails are fully extended, they are straight, the lipid is high, the density is high, there is very less free volume in between the lipid spaces. Now, if we gradually increase the temperature of this system, the fluidity starts to increase, and if we have a temperature above the melting temperature, we have a liquid fluid phase, liquid disordered phase. It is called liquid disordered phase because now there is a disorder to the system. These tails are all randomly oriented, pointing all over the place. The density becomes less, and there becomes more free volume available in between the lipid spaces. Now, if we add cholesterol to this system, liquid disorder phase, what happens is this small cholesterol molecules fill in the gap in between different lipids, increasing the order of the system, introducing a new kind of phase known as a liquid ordered phase. And so cholesterol increases the order to the disordered phase. Now, if we add cholesterol to the gel phase, on the other hand, it also introduces a liquid ordered phase. Now, gel phase is already ordered. So what this cholesterol does is, like with this 4-fused ring, it resides in between different lipid types, and that increases the room in between the lipids, creating like a little bit of more disorder, and you have a liquid ordered phase. So basically, cholesterol has this interesting effect of ordering the disordered phase, whereas fluidizing the gel phase. So this is the role of the cholesterol. Now, we can complicate this system by adding one more lipid species, and this is known as 3-component mixture, also known as the ternary lipid mixture. Now, this triangle I have on the right side of the slide is known as the phase diagram that shows the liquid-liquid coexistence region. The liquid-liquid being liquid disordered phase and liquid ordered phase can coexist in this region. Basically, different points in this triangular phase diagram represent the concentration of different lipid component. In this case, it's a DOPC, DPPC, and cholesterol. So if we're at the vertex, we have the maximum cholesterol of a component. And this region has both of these phases coexisting. Now, one way to study about these different coexisting lipid phases is to use a fluorescence technique. Basically, what we do is we put a fluorescence dye over there, we shine some light, and then the light is gonna be absorbed and the molecules are going to flourish. And we look at this image, and we can distinguish between the liquid disordered phase represented by the bright region in this diagram, and the liquid ordered phase represented by the darker domains, as you can see here. And so basically, as we move along this coexistence region from region 4 to 8, we see that there's more liquid ordered phase than the liquid disordered phase. Now the question is, how do we interrogate the fluidity in lipid mixture? How can we study about these two different kinds of lipid phases? Now, it turns out we can use a polarity sensitive fluorescence dye, and that's what I'm going to be talking about in the next slide. The molecule you can see on the slide right now is a polarity sensitive fluorescence dye named as Laurdan. If we do not consider this hydrocarbon tail and look at this shorter version of this molecule, this is known as a Prodan. So throughout this presentation, I'll be talking about the results I obtained in Prodan for the calculation in Laurdan, but both of these basically have a same chemistry of the chromophore. So this molecule has a donor consisting the nitrogen here, and then the acceptor, which is the carbonyl, and it has like a fatty acid tail. The reason this molecule is helpful is that it is sensitive to the polarity of the environment. So basically, if we look at the emission spectrum of the dye, so this is the emission spectrum of the dye of the Laurdan in the two different lipid type, the one being like fully extended tail, like the gel phase, which is also known as solid phase. There's like very less free volume in between the lipids. And in that kind of phase, if we have this dye and look at the emission spectrum, we see that the emission spectrum is more energetic. But on the other hand, if we place the same dye in the liquid phase, in which there's like a more free volume in between the lipids and the tails are all randomly oriented, then we see that the less energetic emission spectrum. And the shift of this spectrum is 15 nanometer. So we are interested in studying this dramatic shift of 50 nanometer of the Laurdan in liquid phase compared to the gel phase. And one way this is explained, this is now typically explained by the process known as solvent relaxation. So in this cartoon diagram, this horizontal line below is, this is a ground state of the dye. Here I represent the excited state of the dye. Red oval is represents the dipole moment of the dye. And the smaller arrows are the polar solvents that are present in vicinity of the dye, close to the chromophore. Now, when the dye is excited, we see that in the excited state, the dipole moment of the dye increases significantly. The reported values on the literature is like from 5 dBi typically in the ground state to something like 10 to 20 dBi in the excited state. So upon this significant increment of the dipole moment, all these solvent dipoles have to reorient. And then there takes this interaction between the solvent dipole and the dipole moment of the dye. And this process takes about like few hundreds of picosecond. And this process reduces the energy of the probe. Hence, the emission energy is less energetic than the excitation energy. Now, this process I just explained takes place more in the liquid phase compared to the gel phase. Because in the liquid phase, remember, there is water both above and below the bilayer. So in the liquid phase, as there's like more randomness, there's like more free volume in between the lipids, the hydration of the water is more around this dye, like water can partition better in this membrane. So this process takes place more effectively, and hence the energy of the probe is reduced due to the solvent relaxation. Whereas on the other hand, in the gel phase, it's like more tightly packed, less water molecules. So around the dye, and then the emission is more energetic. Now, this shows how the polarity of the solvent can influence the emission spectrum. Now, it turns out that it's not only the polarity, there could be the factor like solute-solvent interaction, which is as important. Now, from the literature, from the experimental measurement, we see that if we look at the emission spectrum of a Prodan in two different solvents with a similar polarity, they are like comparable polarity, but their hydrogen bonding ability is different. The experimentalist they showed that the maxima of the emission spectra is different. So it turns out that it is like more complicated, that the hydrogen bonding can also make a difference. Now we want to study about these kinds of dye to capture all this kind of effect. So what we need to do is we need to understand about the nature of the emitting state, excited state, from which the dye emit. The figure in the slide shows that here's the ground state of the dye in the ground state, and upon excitation, the dye goes to the excited state. Let's say the first excited state. And if the dye is in a gel phase, remember the gel phase is a phase in which this is like very compact, like less water molecule around the dye. The dye emits from the locally excited state. So typically upon excitation, dye reaches the locally excited state first, and in presence of the solvent molecule, which there is going to be in a liquid phase, as like more water can penetrate in the liquid phase, being available near the dye. So the solvent relaxation process I explained in the earlier slide can take place like a few hundreds of picosecond time scale. And because of this, the locally excited state starts to evolve into something called intramolecular charge transfer state. So what happens is this charge can transfer from one end, the donating species, to the accepting species, and the charge transfer state takes place, known as intramolecular charge transfer state. Now, we want to study about this. So the time scale of this time scale here requires us to capture the dynamics of the solvent relaxation, but we cannot do the quantum calculation for this. So we need to do molecular dynamics simulation here. On the other hand, this problem requires the quantum calculation, because we have to calculate the excited state and then the evolution of the excited state, and we need to calculate the absorption energies and the emission energies. So we have to use this MDQM approach. So molecular dynamics for the dynamics of the solvent and the system, and the quantum mechanical calculation, numerical quantum mechanical calculation, to get this excited state of the dye. However, we also have to be careful that this QM calculation, or the quantum calculation we have to run, should be good enough to capture not only the locally excited state of the dye, but also the charge transfer state. So basically, what I have said until now is like lipids can exist in two different kinds of phase: liquid ordered, liquid disordered phase. And in these two phases, we can, to study about these two phases, we can use polarity sensitive dye. And to capture the spectral properties of this dye, what we need to do is we need to run MDQM calculation, in which the QM calculation has to be good enough to capture both the locally excited state and then the charge transfer state. So typically the MDQM calculation, in this kind of calculation, we keep this dye in the QM region, because like we cannot include all of these in the QM, all of the solvents in the QM region. So what we do is we embed this dye that we treat quantum mechanically in the background of the uh, static point charges. Basically, all of this nucleus of the solvent is represented by the static point charge, and we run the QM calculation. Now, for the solvent dynamics of the solvent and the system, we use the classical molecular dynamics simulation, like I mentioned in the earlier slide. This slide shows the workflow of my calculation. So basically, we start with the classical molecular dynamics simulation for some time. And we do this because we want to capture the heterogeneity of the environment. So what we do is we randomly sample different configurations from the trajectory of the molecular dynamics simulation. And what we do is, in each of those configurations, we parallelly run this quantum calculation. I'm going to explain it in a bit. This quantum calculation to find the absorption energies. And then once the dye is excited to the first excited state, we capture the emission energy from the first excited state to the ground state. And then the solvent has to respond and relax, and like there's a dynamics that we capture by classical molecular dynamics simulation, and for the duration of 1 picosecond. And I mean, this choice of 1 picosecond is in a way ad hoc, but we have systematically verified by choosing other choice of the MD duration time that we don't need to go below 1 picosecond relaxation. So we have to run classical molecular dynamics simulation in our in my workflow. So in the next slide, I'm going to briefly talk about the classical and molecular dynamics simulation. This diagram represents how the classical molecular dynamics simulation is done. We use this simulation to study about the dynamics and different properties of a system. The very first thing we do is we build a system. So basically, we build a box in which we have like a many atoms and molecules. Typically, in my case, like 100,000 particles. We build the system, and then we initialize the system with some velocity for the temperature that we want to simulate. And what we do is we calculate the force acting in between different particles and different atoms in the box. So to do that, we take this negative gradient of the potential. Potential usually consists of the bonded part and the non-bonded part. The bonded potential basically describes the covalent chemistry of the system, whereas the non-bonded part can explain solvation as well as the partitioning. So non-bonded part has a Lennard-Johnson potential and the electrostatic. The Lennard-Johnson potential is typically used as 12-6 potential, in which the first part is a repulsive and the second part is the attractive. Now, the Coulomb potential, on the other hand, is like the poor man's model of the electronic distribution. So basically, the partial charges in the MD simulation capture the ground state electronics of the in the MD simulation. And whereas all these parameters involved in these equations, the set of those are known as the force field. And we have to be careful when we are simulating something, we have to be careful about the choice or the accuracy of all these parameters, because the quality of the simulation depends on the accuracy of the force field. Also, the another aspect of the method that I have used is this quantum mechanical calculation known as GW-BSE. And in the next slide, I'm going to talk about it. Basically, we run GW-BSE calculation in 3 different steps. The first step is to use the density functional theory. We solve the Kohn-Sham equation to find the eigenenergies and the wave function and the eigenvectors. And typically, the DFT is good and reliable in predicting the ground state properties. However, interpreting these energy levels we obtain in the DFT as a single particle excitation is misleading because of the self-interaction error as well as the lack of screening of an excitation. And also the gap between the lowest unoccupied molecular orbital and the highest occupied molecular orbital provided by the DFT calculation doesn't agree with the experiment. So what we do in the second step, we use this GW method, in which we replace this approximate exchange correlation functional of DFT by something known as the self-energy operator. And the self-energy operator is within the GW approximation. Basically, the self-energy is a convolution of the Green's function and the screen-Coulomb interaction, and we are ignoring the vertex correction, the higher order term. The screen-Coulomb interaction is written in terms of the inverse of the dielectric function and the Baer-Coulomb interaction. And by solving this equation, we can correct the energy levels we obtained from the DFT calculation, and the gap between the HOMO and the LUMO becomes better and agrees more with the experiment. But this kind of single particle excitation we obtain from here is good to represent the charged excitation. The charged excitation being if we remove electron from the system, like photoemission, or if we add electron to the system, inverse photoemission. For those kind of things, this framework is good enough. However, if we want to treat neutral excitation, meaning the electron gets excited, but it does not leave the system. In that case, the electron is going to be coupled to the hole it leaves behind as it gets excited. To describe this, we have to go beyond this GW theory. So what we do is in the third step, we solve the Bethe-Salpeter equation. To do that, what we do is we have to first write this coupled electron hole excitation, the S excitation, as a linear combination of the quasi-particle product of these states that we obtain in the second step. And then we solve the Bethe-Salpeter Hamilton equation, the Hamiltonian, to obtain the correct energies of the excitation and the states. So basically, the absorption energy here is not the gap between the LUMO and the HUMO, but it's smaller than that because of this term, which is due to the interaction between the electron and the hole. So one thing I want to emphasize is that this method is reliable in predicting both the localized as well as the charge transfer excitation I briefly mentioned in a few slides ago. Now, in the next slide, I'm going to share the result of my calculation, basically this MDQM calculation for Prodan, which is the dye I showed you earlier with a shorter tail in the simpler system, the bulk solvent. So here is the workflow I have already described like earlier, but just to mention it quickly, we run the classical MD simulation for 300 nanoseconds. And from this, from MD simulation, we can capture the heterogeneity of the environment. And what we do is we sample different configurations randomly. And in each of those samples, what we do is we calculate the absorption energy from the ground state to the first excited state using a GW-BSE. Then we calculate the emission energy from the first excited state to the ground state, also by using GW-BSE. Now we want to let the system relax, but the dye is now in the excited state, so we have to have some way to map this excited state electronic distribution to be used in the force field. So what we do is we extract the partial charges of the dye in the excited state by using this module called CHELP-G module, which is basically a way of obtaining a partial charge by reproducing the molecular electrostatic potential. And with this set of partial charge that represent the excited state of the dye, but we use everything, all the other parameters from the ground state except the partial charge. What we do is we let the system relax. We run the MD simulation up for 1 picosecond. And after 1 picosecond, we loop and we do this emission energy calculation again that evolves the system. And then we need to again find the new set of partial charge that represents this newly evolved system. And we do the classical molecular dynamics simulation one more time. And then we iterate until our results start to converge. So basically, if we do this calculation for a Prodan, for the dye I mentioned, in the bulk solvent of different polarity, right? So what we expect is that the emission energy wouldn't decrease much for non-polar solvent, whereas for the polar solvent like water, we expect it to decrease more. And if our results converge, we expect it to plateau as well. And about the excited state, if we look at the dipole moment of the dye in the excited state, we expect that to increase because of the charge transfer in the presence of the polar solvent, and we don't expect to increase as much in the non-polar solvent. And that is what we see in this figure. So figure A shows the excited state, the first excited state dipole moment of Prodan in solvent of different polarities. The most polar solvent here is water, and the least one is hexane. And the y-axis is the dipole moment. X-axis represents this 49 iteration of 1 picosecond of the MD duration, MD simulation. So it's like 49 picosecond in the x-axis. And we see that the dipole moment of the dye increases very little for the non-polar solvent like hexane, and it stays constant. Whereas if we do the same calculation for the dye in presence of water, the dipole moment of the dye significantly increases here, and then it plateaus, it converges. And there are other solvents which follow in between the hexane and the water, and we see that they all follow the trend. Now, figure B is the emission energy of the dye from the first excited state to the ground state. And here we see that the emission energy decreases the most for dye in water, and then it converges. For the hexane, it doesn't decrease much, it decreases a little bit, and then it stays, it also plateaus. And the trend agrees for the other solvents whose polarity is in between these two solvents. Now, one thing we could do is we could also look at the spectra. We could look at the absorption spectra and the emission spectra. So what we've done is we have the absorption spectra and also the emission spectra at the beginning of this process and the end of this process. That's what I have in this figure. So basically, I have the absorption spectra to the left in all of these sub-figures, and the emission spectra at the beginning of the process at 0 picosecond is in the middle in all of these sub-figures, Whereas for the emission spectra at the end of the process at 49 picosecond is the solid curve to the rightmost. And we see that in these different subfigures, as the polarity of the solvent increases, the emission spectra of the dye starts shifting to the low energy region as we expected. So the gap between this emission at 0 and the emission at 49 picosecond increases as the polarity of the solvent increases. And that is what we did expect to see according to our earlier discussion. This is the result from the simulation. But how does this result compare to the experiment? So in the next slide, I'm going to show the comparison. On this slide, I have the comparison of our spectra for the protein, both absorption spectra and the emission spectra, represented by the solid line for the simulation and the dashed line for the experiment. I have compared this with the experimental measurement. And we see that one thing I want to mention is that we are interested in the shift between the absorption and the emission spectra. We are not interested in the absolute position of the peak. And one thing we see here is that in all three of these cases, we have a very good agreement of the shift in both simulation and the experiment. Basically, the spectra to the left is the absorption spectra to the right is the emission spectra, and the difference between the two is the Stokes shift. Now, we can also compare the Stokes shift from the simulation to the experiment if in more cases of more solvents, and that's what I have in this figure. The y-axis is the Stokes shift obtained from the simulation, whereas the x-axis is the Stokes shift obtained in the experiment. And we see that the agreement between the simulated Stokes shift and the experimentally measured Stokes shift is very good. The straight line in this figure represents y equals to x, the line with the slope 1. And we see that this method, MDQM method we've used, gives this result that agrees with the experiment. But this is the steady state behavior. How does the time resolved behavior or the dynamics compare to the experiment? And that is what I have in the next slide. So in this slide, I compare the emission energy of the simulation result shown in different colors with the experimentally measured ultra-fast measurement experimentally obtained for all three cases represented by the black lines. And note that the y-axis for the simulation is to the left, and the y-axis to the experiment is to the right, and the x-axis is the time, basically. And we see that the agreement between the simulation in all three cases, acetone, ethanol, and methanol for protein, agrees very well with the experiment. And I'm saying this, not only it agrees qualitatively, but also quantitatively. Even though I have used like different axes here, I'm saying the agreement is also good quantitatively, because for this kind of measurement, obtaining this kind of agreement is considered to be good. And from all of these from all of these results, one thing we can obtain is we can obtain the relaxation time. So what we can do is we can use the multi-component like exponential function. We can fit this and we can obtain the relaxation time. And this is what I show in this table. So basically we have like the simulation and the experimental like result for protein in all these different solvents, and we have the relaxation time from the simulation and also from experiments in like most of these cases. And if we carefully look at these numbers, we see two trends. First, we see that for hexane, acetone, and water, there's only one relaxation time, and not only for the simulation but also for the experiment, and the comparison is good. Whereas if we consider these alcohols, octanol, ethanol, and methanol, we see that there are two relaxation times, also in the experiment and also in the simulation. And this is interesting. But like this great qualitative agreement in the simulation and the experiment. However, quantitatively, if we look at the numbers kind of look like, oh, they are different, and some of the errors are like too big. This is especially because of the difficulty of this nonlinear fitting to the simulation data, which is basically very noisy. And all of these measurements I've been showing until now are done by Matthew Phillips, who graduated from the Gundlach group, and Professor Lars Gundlach at University of Delaware. So what I have shown until now is that we have used MDQM method for protein in this bulk solvent of different polarity, and we have validated the result of our simulation with the experiment, and it turns out that this method agrees extremely well with the experiment. And this calculation is productive and quantitative for the bulk solvent. But what we are interested in is like more difficult problem. We are interested in this spectral properties of Laurdan. Remember, Laurdan is the protein with like a longer hydrocarbon tail, and the longer hydrocarbon tail is there to make it easier to partition in the membrane. So, but we are interested in the spectral properties of the dye in the membrane, and that is what we are after. But before showing the result of MDQM calculation of Laurdan in the membrane, I'm going to first show some of the behavior of Laurdan we obtained from classical molecular dynamics simulation. So what we did is we ran the simulation of this dye, Laurdan, in a different system of two kinds of system. One is liquid disordered system. From our earlier discussion, I have mentioned that in liquid disordered phase, these liquid tails are randomly oriented. They are pointing all over the place. There's like more free volume in between the lipid spaces. And the liquid ordered system, in which like it's like more compact, more ordered, less free volume in between the lipid spaces. So we have ran the MD simulation of this dye in both of these systems in two kinds of ternary mixture. And in all of those simulations, we see a typical behavior that in liquid ordered phase, which is this phase, we see this Laurdan likes to stay upright and vertical most of the times, although there are few configurations in which the Laurdan could tilt. However, in the liquid disordered phase, we saw that this Laurdan likes to typically tilt, perhaps because there's like more free volume in between the different lipids. So there's more room for Laurdan to tilt, and this is the behavior we see. So if we do measure the angle between the dipole moment of a Laurdan, and the dipole moment of Laurdan is along this direction, pointing from this oxygen towards the nitrogen. If we measure this angle, with respect to this z-axis, the parallel to bilayer normal, we expect that the angle be greater in liquid disordered phase compared to the liquid ordered phase. And this figure shows exactly that. So we have these two systems, ternary mixture of DPPC, DOPC cholesterol, PSM, POPC cholesterol. One type represents this ordered and the other is disordered. And we see that in disordered phase, this distribution of the angle I explained here is very large actually. It's like it likes to like totally tilt for both disordered phase. And in the liquid ordered phase, we see that although there is like this second bimodal distribution here, we have like this part where in some of the configurations Laurdan could tilt, but mostly Laurdan is staying upright and vertical. And we see this also in this other liquid ordered phase. But interestingly, here's like this part, this first bimodal part is in the lower end. We see this. The another consequences of this Laurdan tilting in the disordered phase is that this nitrogen, which is here in the head group region of a Laurdan, like goes deeper in the membrane in the liquid disordered phase because it tilts. Whereas in the liquid ordered phase, it's staying upright. So it would be more towards the interface in the ordered phase. And that is what we see in this figure. So for both liquid ordered and disordered phase, I have a result. Red curve here is the Z position of nitrogen in the Laurdan, and the blue represents the average position of a nitrogen of a lipid. So we can compare where does the head group of this molecule reside with respect to the average position of the nitrogen in the lipid. And we see that in the disordered phase, this dye likes to penetrate deeper inside the membrane from both sides. So we see this because of the tilting behavior. Another consequence of the tilting of the Laurdan in the liquid disordered phase is that as Laurdan tilts, the oxygen which is here, the oxygen of the Laurdan is more closer to the bulk water, so it would be better solvated by water. Whereas in the liquid ordered phase, since the nitrogen is way up here, the nitrogen would be better solvated. So if we look at the radial distribution function, we see this in the LD, like a LD bilayer, LD system, the oxygen is better solvated than the LO, whereas the nitrogen is better solvated in the liquid ordered phase, because it is vertical and nitrogen is closer to the bulk solvent. And one thing I want to emphasize here is that this behavior of Laurdan tilting in disordered phase is actually unexpected behavior for Laurdan. So what we expected was, we thought this Laurdan would be more towards the bulk water, more closer to the interface, because this shift in the emission spectrum in this system is typically because of the presence of water molecule in the vicinity of the chromophore, so it would be better solvated. That's what we expected, but what we saw was unexpected behavior. Now, in the next slide, I'm going to show the MD result of the MDQM calculation of Laurdan in the lipid membrane. So basically, we have two systems here. One represents the more ordered system, a 50-50 mixture of DOPC and cholesterol, and other is like the liquid disorder system, only containing DOPC, and we have a Laurdan here. So what we did was that we did this MDQM calculation. We have already validated for Prodan, and this figure I am repeating here. I have already shown it that the emission spectrum we expect to be more energetic for like more ordered system, whereas for the less ordered system or the liquid system, we expect this spectrum to be less energetic. We expect to see the shift. Now, what happens here? So we ran this calculation following the workflow I have described earlier. So this time we have this MD simulation of Laurdan, from which we sample more configurations than in the case of the bulk solvent, especially because of the complication, because the membrane is very heterogeneous. And in each of those configurations, we parallelly run this GW-BSE calculation, calculate the absorption energy, then we calculate the emission energy. And what we do again is we obtain this set of partial charge to map the excited state electronic distribution to be used in the force field in the MD simulation. So we obtain the partial charge for this dye in the excited state by using CHELP-G scheme, again to reproducing a molecular electrostatic potential by adjusting a partial charge. And with this, we let the system relax for 1 picosecond again, and we iterate, and then we do the quantum calculation again. So we alternatively, we evolve the excited state, calculate the emission energies, then relax the system. And we do this until our result start to converge. And this is the result I've obtained. The figure A is the dipole moment of Laurdan in the excited state. And the x-axis here is again this iteration 1 picosecond each. So this is like the 19 picosecond. And we see this, the dipole moment of the dye increases more for the liquid ordered phase compared to the liquid disordered phase. Whereas the emission energy decreases more for the ordered phase compared to the liquid disordered phase. Now, this behavior here indicates that there is more charge transfer taking place in the liquid ordered phase compared to liquid disordered. But in reality, what we expect to see is that this thing would be more for the liquid disordered phase. Basically, the gap between the shift of emission spectrum between the more packed phase versus randomly like a disordered phase, here 50 nanometer from the experiment, in our calculation we obtain this difference of the emission energy as 47 nanometer, but the results are backward. So we didn't get the result as we expected to see. We actually got the reversed result. Now, at this point, I would like to say a few things here. Firstly, we obtained this unexpected behavior of Laurdan in the disordered phase. We expected Laurdan to be more solvated and be closer to the interface, but we saw that tilt we are not expecting to see. Now here, when we use this MDQM calculation, which works extremely well, we have already validated this for the bulk system with the experimental result. Here is giving us the reversed energies. So here now we ask a question. So what should be the correct partitioning of this? Where should Laurdan actually be? Should it be deeper inside in the LD phase, or should it be more closer to the interface? Now we question here, is this MDGW-BSE calculation we run sensitive to the position of a Laurdan along the axis parallel to the bilayer normal? So basically, when we do this MDQM calculation, we randomly sample configurations and we run configurations in run the calculation in all of those configurations, right? So, but then when in those configurations we randomly sample, in some of the cases dyes could be way up here closer to the interface to the water. This slab here represents water, or like way closer to the water, or the Laurdan could also be in the configuration where it's deep inside the membrane, in between both interfaces. And we could see this as well. So is our method sensitive? If we shift the Laurdan in along this direction, can our method report the change? So to test that, what we did is, without spending much time here, so what we did is we sampled the configurations in which Laurdan are close to the interface. We avoided the configurations where Laurdan is inside here. So what we did here is, like, we biased sample only these configurations, and we see this, the emission energy of the Laurdan shifts in the direction we expected it to shift. So in the correct direction, we expected to see this, and the shift correspond to 93 nanometer. So it's good that not only that this MD-GW-BSE method is good and compares very well with the experiment, it is also sensitive to the position of this Laurdan, location of the Laurdan in the Z direction. So now, but what should be the ideal behavior for this molecule? Where should it actually partition? So one way we could study this by running this rigorous free energy calculation to understand where would the Laurdan like to partition in the membrane with the current force field that we are using. To do this, we decided to run free energy calculation, adaptive biasing force calculation. And this ABF calculation, with the help of this rigorous ABF calculation, we expect to see this partitioning behavior of Laurdan with the force field, with the model that we're currently using in our MD simulation. So basically, the calculating the free energy is a fundamental problem in biophysics. By knowing about the difference in the free energy, we can learn about different processes such as protein-protein interaction, protein-drug interaction, the partitioning behavior of a drug in the cell membranes. In my case, I'm interested in the partitioning behavior of protein in the lipid environment, which in my case is a box of hexadecane molecule. So basically, the free energy can be written in terms of the natural log of this probability distribution function, and calculating this absolute value of the free energy is a difficult task because that requires us to compute the partition function. Therefore, it is difficult. However, fortunately, for most of these processes we are interested in, we only care about the difference in the free energy. And the one way to calculate the difference in the free energy is by using this thermodynamic integration, in which what we do is we calculate this derivative of a free energy with respect to some transition coordinate. And this transition coordinate would depend from problem to the problem we're trying to solve. And then we integrate this gradient to obtain the difference in free energy. However, during our simulation, we are still wanting the system to sample both of these states we are interested in, state 0 and state 1. But like there could be like a very high free energy barrier in between these two states. So the system may not sample both of these states, or like one has to run very long simulation. And even with that, there could be poor sampling, because we see here, if this free energy value is greater, the probability is going to be less. So unbiased simulation suffers from poor sampling. And one way to solve this is to use adaptive biasing force, ABF calculation. So what happens in this calculation is we calculate this gradient, which is a generalized force. And what we do is we add the negative of this force to the system. And what that does is that flattens the free energy barrier, allowing the system to make a progress in the direction of a transition coordinate. So basically, calculating this quantity is basically computing the partial derivative of the Hamiltonian with respect to the transition coordinate, and this whatever we obtain here, and negative of that is going to be our adaptive biasing force. That force we apply to the system to flatten the free energy barrier. So basically, ABF calculation works in two steps. First, we measure the gradient. This is what we measure. And we integrate the gradient to obtain the potential of mean force, PMF, or potential of mean force, is basically the free energy in the direction of the transition coordinate. And after obtaining this, we apply the biasing force. We apply the biasing force to flatten the free energy barrier. Now, in my case, this figure to the right I'm showing here, it shows the box of hexadecan molecule, uh, which is surrounded above and below by the slab of water. So this is like 1100 water molecules, 500 hexadecan molecules, and this represents this hydrophobic lipid environment. And this is the direction of the transition coordinate. And transition coordinate is defined by the projection of distance between center of mass of protein, this is a protein, and the center of mass of the hexadecan box projected into this direction. That's the transition coordinate. And in practice, when we run these simulations in computers, what we do is we divide this transition coordinate into different intervals, and each of which is 0.05 angstrom. And we measure the gradient, we integrate to get the PMF, and then we apply the biasing force, allowing system to make a progress in this direction. Now, in the next slide, I'm going to show the result of this ABF calculation in the 6 different replicas, started with a slightly different initial condition, and run in the simulation of total simulation time of 2.1 microsecond. So basically, these 6 PMF, the y-axis here is PMF, x-axis is the transition coordinate, 0 is the center of the hexadecan slab. So all these curves are the PMF obtained from these 6 replicas, and the total simulation time of which is 2.1 microsecond. And here we see that the result of all these different PMF in all these different replicas are starting to show this valley in the same region on both sides. So our simulation result had already started to converge. So now one thing we can do is we can combine all of this PMF to obtain the combined PMF, and that is what I have in this figure. For the ease of the viewer's eye, I have overlaid this graph of the result of the ABF calculation on the top of the MD snapshot. And to be faithful to the scientific community, here is I have mentioned the distance between the 2 atoms. The center here is the center of the slab. So the y-axis to the left is the PMF, combined PMF of all these results, and the y-axis to the right is the uncertainty in the measurement. And we see that the black curve is the error and the red curve is the PMF. Now, one thing we notice here is that this red curve, which is a PMF, is not symmetrical yet. So this means that I have to run this calculation for a longer time to fully converge the system. And as I'm speaking today here in front of you, this calculation is still running, and after running it for some time, I expect this to be symmetrical. And the problem of this convergence I can still show from the error, because the uncertainty is still high. So that I expect to decrease after the simulation converges. So what I see here is that even though this is still running, we can already look at the behavior of protein and where it likes to partition by looking at the position of this valley in this PMF. And we see that the protein likes to reside like deep inside the interface. The interface is represented by 2 vertical blue lines. And here this is like minus 28 angstrom and the plus 28 angstrom. That's the interface. And we see that the protein likes to reside like deep inside here, like 10.2 angstrom away from the interface in both ways. So no wonder this current force field that we have used in our MD simulation as well as in MDQM calculation is hydrophobic for protein, so that the protein likes to be in this hydrophobic region. So yes, when there is a liquid disordered phase, like there's more room, the Laurdan likes to go inside, it likes to tilt, it likes to be in like in between the interfaces. And that, because our MD GW-BSE method is very sensitive to the position of the Laurdan in that direction, yes, and then the result we obtained was that the energy was incorrect. So we can use this calculation like ABF calculation to understand how is this current force field behavior give the partitioning of the protein. And basically now with this calculation, with the ABF, which is a robust way of finding free energy, And with this MDQM, which is very good, compares well with the experiment, and it's also sensitive to the position of the protein, we can go back and improve our force field. So to summarize, firstly, I've explained that Laurdan and Prodan, they provide an effective way to interrogate the structural difference, learn about a different phase, liquid ordered phase and liquid disordered phase. Whereas on the other hand, this MDGW-BSE method, this iterative calculation I've developed, and provides a accurate way and accurate spectral properties. It gives the accurate spectral properties and also agrees very nicely with the ultra fast measurement. So basically, I've run this GW-BSE calculation using Vodka XTP. For DFT part, the Gaussian was used. For MD simulation, most of these were on GROMACS, whereas the ABF was done on MD. And this MDGW-BSE calculation gives us very experimentally agreeable spectral properties in the protein in the bulk solvent, whereas for the Laurdan, we still need to improve our Laurdan force field. And for that, we can use this adaptive biasing force calculation, which is ABF calculation. That's a robust way of finding free energy profile of the protein. We could use all of these to further improve the force field, accuracy of the force field in the future. And the one way we could do that is capture the cation pi interaction. We know that from the literature, we know that the cation in the lipids can interact with the pi in the protein and Laurdan, and the strength of this interaction is as energetic as the hydrogen bonding. So this is important, and there are ways we could improve the force field by tweaking the LJ parameters, the NV fix and things like that. We could include this, and we could also include hydrogen bonding. In the introductory slides, I have already shown that hydrogen bonding plays an important role. It can make a difference in the emission spectrum. Now, I have implemented hydrogen bonding in the absorption calculation, but I have not included this in the emission calculation yet. So in the future, this is something we can add. And finally, with the better accurate force field, we could repeat this calculation for the Laurdan in this lipid bilayer again. So basically, the way I think of this research here is not like a movie that ends and ends, but with a movie that can have a very nice sequel. So basically, and in my personal opinion, the sequel of this work is going to be even more exciting. Finally, please allow me some time to thank people that have really helped me to make a progress throughout my graduate career. I want to thank my direct supervisor, Dr. Edward Lyman, for teaching me how to do physics and supporting me. I also want to thank Dr. Björn Baumeier from TU Eindhoven, who basically taught me how to do this GW-BSE calculation, who is also my co-advisor. I want to thank Dr. Sandeep Patel. He was the one who really motivated me about the usefulness of Laurdan in the beginning days, and he also funded me for an entire year to run this kind of calculation. I want to thank Dr. Lars Gundlach for providing very insightful discussions every time we had a combined group meeting, and also collaborating with this ultra fast experimental technique that I could compare my simulation result to. I want to thank Dr. MacDonald for not only being the part of my committee, but because he was the first person I contacted when I applied to the graduate school at University of Delaware. And that was 2 times, not just 1 time. When I applied to UD, both times, he was the first person I contacted, and he really encouraged and supported me. I want to thank Dr. Jeffrey Comer from Kansas State University for teaching me everything I presented today from this free energy calculation, ABF calculation. My thanks to Dr. Alex McCrell and Dr. Fang Yu from University of Maryland. They helped me how to parameterize or optimize the partial charges I have used in this MD simulation. I want to thank the Lyman group from 2015 and 2020, all of the members, past and present. I want to also especially mention Mitch Dorrell and Allison. They were really helpful about giving me feedback about my slides and stuff. Thank you, guys. I want to thank the IT office, Samsung and Solab, because they were the one that really helped me with the computational problem, because I was not good computationally when I joined the group. I want to thank DPA in general. I want to provide acknowledgement to my family and friends, my parents watching from Nepal, my siblings watching from California, my friends, relatives, mentioned my mother. She was the first person to support me when I decided to come to United States after my high school to study physics. I want to thank my mom, my father for supporting me, my sisters and my wife for dealing with me on a daily basis. I want to thank PADS, which is a Physics Graduate Student Society, for allowing me to serve as the vice president of this organization and also organizing all these fun events. I want to thank graduate student government for allowing me to be the senator representing physics department. And it was a really fun being there. I want to thank Nepalese Student Association for all the help during my stay in Newark, Delaware, and also allowing me to serve as the president of Nepalese Student Organization, and mention the thanks to all the grant and computational resource I have used throughout my calculation. Thank you very much. And I want to stop here.
Okay, great. Thanks, Swapnil. So at this point, we can give a few minutes for any questions from the audience. Like I said, you can ask them in the comments section of the YouTube feed or email me. And I'll just kind of, I have to wait. I think the YouTube feed lags a bit, so I'll wait a few seconds. If anything shows up, I'll pass it along. So far, Swapnil, you're just getting a bunch of accolades and congratulations and a nice talk. Asta says, great job. Subhash says, huge congratulations. Mitch says, nice work. Anyone else? Questions? Shay says, great job. So I guess that means those are coming through the YouTube feed, so people must be aware that the talk has ended. Okay, on questions, going once, going twice. Pratima says, great work. Going 3 times. Okay, nothing in my inbox, nothing in the feed. Okay, so at this point, I'd like to move to the private section of the seminar. Swapnil, you can shut down the YouTube feed to the committee. You can kill this Zoom link, and I just